Hello, everyone. My name is Zhesheng Liu. I'm a PhD student in computer science at the University of Pittsburgh. I'm very happy to present our work along with Licheng Liu, Yitun Xie, Zhenglong Jin, and Xiaowei Zhang, the task-adapted meta-learning framework for advancing spatial generalizability. Here is the background and motivation. The spatial temporal machine learning has greatly emerged in recent years because it has a variety of societal applications such as agriculture monitoring, hydrological forecasting, and traffic management. However, it's rather difficult to solve those real-world problems. The two reasons. The first, spatial temporal data exhibit complex variability across locations. Second, many real-world applications lack sufficient annotated data. We focus on crop yield prediction in the United States. It is an important task that will benefit 100,000 farmers, insurance companies, and subsidies, food supply workers, etc. So the map on the right shows the Midwest of the United States, including 14 states like Wisconsin, Minnesota, Indiana, etc. Each small unit is a county. So the map shows normalized average corn yields in 21 consecutive years from 2000 to 2020 across 630 counties in the Midwest. The dark color represents low yield counties, while light color represents high yield counties. The two takeaways. First, crop yields are highly correlated to locations due to difference in weather, soils, management practices. Second, it has limited data, and most crop yields are reported just once a year. So researchers want to address these two issues use multitask learning. They want to join learn shared representation for multitask to improve the overall performance. However, the crop yields are incompatible towards multicast objectives, as the crop data have rather different distributions. Also, it is difficult to learn shared tasks since tasks are mostly independent in real scenarios. Like a county in Illinois is totally independent of another county in Ohio. Other researchers are interested in meta-learning, like model-agnostic meta-learning, short for MAMO, that learns a base model that can be quickly adapted to new tasks. However, MAMO-based methods have poor performance on a large number of heterogeneous tasks. Also, it has not considered regional discrepancy. To bridge these gaps, we propose a new MAMO framework and have following contributions. First, we developed the first meta-learning framework for real-world crop yield prediction that will have significant social impact. Second, we propose a new meta-learning training strategy that adaptively learn models through an easy-to-hard hierarchy tree. Third, we extend the meta-learning method to handle a large number of heterogeneous tasks. Here is an overview of the framework. It has several components like data loader, predictive model, task formulation, training phase, and test phase. Let's check out the predictive model. We train our LSTM using spatial and temporal information in the crop data. However, the framework is compatible with any universal predictive model. We use LSTM because it's a state-of-the-art model for the crop yield prediction. The next step is to formulate tasks. So each task runs predictive model on the county level crop data. If you recap the map, there are 630 counties. Therefore, we formulate a total of same number of individual tasks. That's a really, really big number. The next step is to do easy and hard hierarchy construction. Initially, we train all the tasks with a standard memo on the first layer. As shown on the right, is the root node of the tree. It has 5 tasks. The next step is to split the 5 tasks into easy tasks and hard tasks, and the train easy model and hard model. So in the second layer, task 1 is an easy task. Task 2 to 5 are hard tasks. The hard tasks in the second layer will be split into another easy task set and hard task set on the third layer until it reaches maximum depth. So intuitively, hard tasks are trained with more iteration than easy tasks. Like hard task 5, we train in first layer, second layer, third layer, and fourth layer. The last hard task will be used as another initial model in the next training epoch. The method we use to split the task into easy tasks and hard tasks will be introduced in the next 2 slides. We conduct a hypothesis test on the task based on their R-square validation performance, where R-square is a metric ranging from 0 to 1, the higher the better for the regression model. The non-hypothesis is that all the tasks follow single normal distribution. Alternative hypothesis is that there is a subset of tasks U having a different normal distribution from the remaining tasks U prime. Check out this 2 normal distribution curve. It is an illustration of the alternative hypothesis. So the object is to find the optimal subset U star, which is the maximalized log likelihood ratio between the subset distribution and the whole set distribution. Let's bring the hypothesis into an algorithm. Suppose U are easy tasks and U prime are hard tasks. So U star can be solved by minimizing the sum of variance of 2 sets. You check out the normal curve on the right. If the variance is low, there will be narrow bell shapes, which is easy to distinguish with each other. So in practice, we select a threshold gamma to divide a task into U and U prime. That is summarized in our algorithm 2 in the paper. Therefore, a task Ti on the hierarchical layer R can be categorized as an easy task or hard task using this formula. For the test task adaptation, test tasks are also divided into easy and hard tasks. We use the same threshold gamma in the training, and the same splitting strategy will ensure the test tasks select the best meta model for adaptation. So the select model are on the leaf node of a hierarchical tree. For the dataset, we use National Agricultural Statistics Services dataset. The data is collected from 630 counties in 21 security years from 2000 to 2020. Each county in each year has 300 data points that include 19 features. So we split county into training and test. The former has 80% counties, the latter has 20% counties. And then we split the years into support and query. Like support set has the first 5 years data, and the query has the last 16 years data. They have 15 data points or 75 data points in each county respectively. For the baseline and models, we evaluate all the model on the test query set. The baseline state-of-art attention-based LSTM, and we also do a comparable memos like original memo, transfer memo, condition memo. And our adaptive memo has 2 versions. These 2 versions are different in terms of inner and outer training epochs. So here is the results. We evaluate on the whole yield, low yield, and high yield counties. Our proposed method outperforms all the baselines and comparable memos. If you look at the column in the middle, it's a low yield county. Our model strongly outperformed baseline by a lot. This is because a low yield county usually have a high data variability. Therefore, our model is able to adaptively learn those hard tasks and ensure it has good performance. Also visualize the county level R-square performance in the test set in Indiana. The first 3 are baselines. The 3 in the middle are comparable memos. The last 2 are proposed mem. So the dark color on those maps has lower R-squares, which is bad. So our proposed model has few of them, which is the best. We report R-square performance over 16 years from 2005 to 2020. The solid lines on this chart shows the adaptive memos that proposed by all. So it outperformed all other models in most years, except the year of 2019, 2020, or 2012. Because our model addressed the issue of the spatial variability regardless of the temporal variability, which will be left at the future work. So next, I show the task adaptation. This map shows the training task's performance. The dark area has low R square. The light area has high R square. So our algorithm is able to distinguish them, like split into hard tasks and easy tasks. So it's very reasonable to see that the map in the middle has a hard task because they have low R squares. If you compare the first map and the last map, the before adaptation, after adaptation, the box area that had the low R squares were greatly improved, while we still remain in excellence in other areas. So for parameter sensitivity, if you look at the red bar, the performance is not changing significantly when we increase the number from 1 to 4 in the x-axis. This is the maximum split depth, which means it is not quite sensitive. If you look at the blue bar, it shows the performance drop. This is because when we increase the inner iteration, the model just got overfitting. So in conclusion, we solved a very important real-world problem and push the boundary of probability prediction. We propose a task-adaptive memo to lower spatial sensitive tasks with even limited data. We demonstrate meta-learning generalizability on a substantial number of heterogeneous tasks. Our code is available online. Please feel free to scan the QR code if you're interested in reading our paper. Thank you.